hi everyone, thanks so much for having me. So as you can see, my name's Jodie Burchell. I'm the data science developer advocate at JetBrains. I live in Berlin, but as you might be able to tell from the accent, originally from Australia. So yeah, my first time in Oslo, it's beautiful. A little cold for me, but very nice. So some of you might be working in NLP already. The previous talk showed that, obviously there's a lot of work going on in this area. For those of you who aren't, you could not avoid the stuff that's coming out about large language models at the moment. So some of the most famous examples are Google's Lambda model, which one of the engineers thought had achieved sentience. It hadn't, spoiler alert. Or you might have seen GPT-3. If you haven't played with that, there's an amazing endpoint that OpenAI is offering. It is so much fun. Or you might have played with Copilot. So if you haven't worked in NLP before, you might have wondered, how are these models created? And stepping back a point, you might have wondered, how can you take raw text data and turn it into something that machine learning models can understand? So in this talk, I'm going to be going through two of the most commonly used methods, word embeddings and transformer-based architectures, and just giving like a 1,000-foot view of how they work, as well as some examples of how you can use them in Python. So to give like a very kind of low-level introduction, when I started my post-academic career in data science, I actually went straight into natural language processing. But prior to that, I was working in health sciences, and everything in health sciences is tabular. So I was really used to data being in this format, where you have every single row representing an observation, and of course, you have your feature columns. So what I'd learned is that models can only accept data in this sort of format. So this is a little bit low level for this audience. I gave this at a Python conference, so we'll just quickly go through this. So if you take an example of a model that's using tabular data, obviously you have an input node for every single specific feature column. So let's say we're trying to predict whether a house sells or not. So obviously we'll have an input node that's going to expect, say, the first column, the number of rooms that a house has. The second input node is going to expect the distance to the beach, and so on. But when we come to text data, things look really different. So let's say we're trying to predict whether a headline is clickbait or not. And let's take a look at a couple of sentences. So we have a first sentence, summer's hot shoe trends. And we have 4 input nodes for our model. So far, so good. So we feed every single one of our words into these input nodes. But then we get to the next example, the best Halloween costume ideas. What do we do with this extra word? The sentence is now too long for the number of input nodes we have. And as many of you would be aware of, models don't work with text. They can only work with numeric representations. So this is where vectors come in the context of NLP. All vectors are, in the context of natural language processing, is the conversion of a document into some sort of representation in features. And what these features aim to capture is something about the way that we understand text. It could be the words that the text contains, or it could be the meanings of the words, or it could even be the meanings of the words in context. So we're going to be exploring that in a couple of different ways in this presentation. So the first approach we're going to discuss are called word embeddings. So to start with this, let's take 7 words. Queen, king, girl, boy, woman, man, and tree. So let's take a thought exercise, and let's say we decide to manually group these in a 3-dimensional space. We just have 3 random dimensions. And let's say we put girl and boy together, we put woman and man together, put king and queen together, and over in the corner we put tree. So we take the coordinates of those words in a 3-dimensional space, we get something that looks a bit like this. And we start to see some patterns if we map out them on a heat map. So in this first dimension, we can see that girl and boy have similar values on this dimension, but everything else is different. So maybe this dimension represents something to do with age. On this second dimension, we can see that king and queen are quite similar, but everything else is different. So maybe this dimension represents something to do with class or nobility. And then in this third dimension, we can see that tree is different from all of the people. So maybe this represents something to do with a sense of personhood. So what these values are for each word are word embeddings. And what they attempt to do is capture the meanings of words by seeing how similar or dissimilar they are to each other in a vector space. So, of course, we're not going to create word embeddings manually. That would be an absolute nightmare, especially for very large vocabularies. Instead, we rely on word embedding models to do this. And what these do is learn these embeddings by seeing how words behave in context. So in today's talk, we're going to be using my favorite of these models, word2vec, and specifically, we're going to be using the skipgram architecture if you decide to go and read about this later. So what these models do is they learn these word embeddings by taking all usages of a word and seeing which words occur around it and trying to predict that by seeing many, many training examples. So let's take a very simplified example. Let's take the word best in our clickbait data. So what we're going to ask the model to do is predict which word precedes it and which word follows it. So initially, like all models, the guesses are going to be pretty inaccurate, but as we show it more and more training examples, it's going to get better and better at predicting which word precedes and follows best. So let's say our first training example is the best things. So what the model will see is that the precedes it and things follows it. In the next example, we have the same pattern. But in the third example, we can actually see something slightly different. So what the model is going to learn from this is the word that precedes best is the, with a high degree of confidence, and with a little less confidence that things is the word that follows it. And a really nice property of word2vec models is it turns out that the internal weights, the hidden layer that it uses in order to make these predictions, turns out to be the word embedding for best. We can actually extract that from the model and use it to represent best as a word embedding. We then repeat that for every single word in our vocabulary, and we end up with a word embedding for every single word. It's pretty cool. It's like magic. Okay, so due to the way that the model is trained, it means that words that are in similar contexts, so used in similar ways, tend to have similar word embeddings. So what we can see if we have words like best, worst, and funniest, these are all used in a similar context in our clickbait data. So what it means is that they end up with similar weights on each of the dimensions. In contrast, we have words like war, attack, and blast, and these are all used in different contexts, so they all end up with different weights on each of the dimensions. So what I've been showing you so far are little toy examples of these word embeddings with 3 or 5 dimensions. In principle, we ask the models to create these with generally at least 100 dimensions. The other important thing is, although I've explained these to you with sort of trying to understand what these dimensions mean, we don't really care about that. All we need is that the model can use these dimensions to separate out words that are dissimilar and group words that are similar. So let's now jump over to PyCharm. Of course, I'm going to show you in PyCharm. I'm from JetBrains, and see how we might do this in Python. Okay, so of course, what we're going to do is read in 2 data sets. We're going to have a training data set. We're going to use this to both train our word2vec model and also train our clickbait classifier. And we, of course, have a validation data set to see how well our clickbait classifier is performing. So the first step when you're training a word2vec model is to do a little bit of string cleaning. So this is because word2vec models basically collapse all of the usages of a word to the same token. So you need to normalize the text as much as possible. So you do things like convert all of your words to lowercase, remove all your non-alphanumeric characters depending on your model, and also remove things like additional white space. What you then do is you do one final part of pre-processing, and that is to basically split each of your sentences into a list. So we can see our first training example we're going to use for the word2vec model, which is where essentially we have a lightly normalized list instead of a string. So now we're going to train our word2vec model. We're going to use the amazing Jensen package. This package is so cool. It's just so much fun to play with. And we're going to import the word2vec module. And you can see, like many machine learning models, this is a one-liner to train. So what we do is we obviously pass in that process training data, and we specify a number of hyperparameters. So the first is that we're going to basically create 100 dimension word embeddings. That was just a choice that I made. We can talk about that afterwards, why you make that choice. And another thing that I've done is I've removed any words that only occurred once. Could have been a little bit more punitive with this, but generally things that only occur once, you can't detect a pattern. So now we can see if we train that model, once we query it, we can actually extract that word embedding for best. And we can see it looks really similar to the toy examples I was showing you. It's just that this one has 100 dimensions. Something else that we can do is we can find words that are the most similar to the word best using this most similar method. So you can see that our model has word embeddings most similar to best for the words funniest, cutest, most, and then Twitter, friend, cast. And these are cosine similarities in case you're wondering. But the thing is, we don't actually want to classify words. We want to classify entire sentences. So what do? Well, the simplest thing you can do is because we're dealing with vectors, we can actually average them. So we can take all of the words that occur in a sentence and basically average all of their word embeddings. So that's what we're going to do in this next two methods. So what this function does is it basically takes a headline, it gets every single word, looks up the word embedding, and then if they exist, it appends it to a NumPy array. Then in this next function, what we do is we iterate over every single one of the headlines in our training or our validation set. We check if we've been able to retrieve any word embeddings for that particular sentence, because remember we removed some of the words, some of the rare words, so we don't necessarily have word embeddings for everything. And if that is the case, we average over each of those. So what we end up with is for every single training and validation sentence, we end up with a single 100 dimension word embedding. So you can see for this particular training sentence, we have a 100 dimension word embedding. So now we're ready to train our classifier. So what I've done here is I've actually built a convenience function. Underlying this is just a very simple Keras model. It's just a really simple neural net. All you really need to worry about is the input is those document embeddings, so the average of each of the words for the headline, and the output is whether it is a clickbait headline or not. And what you can see is on that first pass, we're already up to 95% accuracy, which is not bad. But of course, models are most interesting where they fail. So let's see where it didn't predict particularly well. So these are the headlines the model incorrectly predicts are, it says that they're non-clickbait. So you can see some of these are really clear misses, like this one's obviously clickbait. This one is obviously clickbait. But this one maybe is a little bit more about the tone rather than the words used. And you can see a similar thing when you look at the ones that it incorrectly thought were clickbait but are not. So maybe this one is kind of a bit more about the tone rather than the words used. And this is where word2vec sort of fails us. What word2vec does is it basically collapses all of the meanings of a word onto a single token. So let's say we're dealing with a word like bank. You might have, I went to the riverbank, or I opened a bank account. Bank clearly means different things in different contexts, but word2vec models can't tell the difference between these usages. Basically, that embedding would average out the meaning, those different meanings of bank. So this is where the current generation of models come in, and these are all based on a particular type of architecture called transformer models. So let's start with a really simple example of how these models work. So we'll start with this example sentence. He checked his bank account. So we start where we left off. We basically create word embeddings for each of the words in that sentence. But what we do next is we weight them based on their position in the sentence. So we create positional vectors for each of the words, and we alter slightly each of the weights for their word embeddings on each dimension. What we then do is a process called self-attention. So we retrieve different vectors from our positionally weighted word embeddings. And what we do is we do a process that essentially works out these self-attention vectors. So let's have an example, let's have a look at what these actually are. So if we have a look at the the self-attention vector for the word bank, what we can see is these weights essentially represent how much attention the model needs to pay to other words in the sentence in order to understand what the word bank means. So this is he checked his bank account. You can see that it obviously needs to pay the most attention to the word bank to understand the word bank. But it also works out that it needs to pay quite a bit of attention to the word checked and the word account. And that's because this gives clues about what bank means in this context. So essentially, self-attention mechanisms tend to have this bias to focusing on the word itself when working out the meaning. So what these models do is a process called multi-headed attention. So they repeat this process multiple times. They combine all of the different self-attention vectors, and then they do a normalization process. And this entire self-attention block with the multi-headed attention normalization is called an encoder block. So this leads us to the specific transformer model that I'm going to be talking about and we're going to use to classify our clickbait headline, and this is called BERT. So if you hadn't heard of it, that's why I had a Sesame Street character at the beginning of the presentation. So the researchers have had a lot of fun with this, riffing on these names. So I think my favorite is Camembert for the French BERT model. They're really, really cute. So BERT is a really cool model. It's a general purpose language model, and it can do a whole bunch of different tasks and do things like text summarization, question answering, and for our purposes, text classification. So how does it do this? It's all to do with how BERT was trained. So BERT was trained to do two different tasks. The first thing that it was trained to do was work out whether, if you have two sentences, does the first sentence entail the second one? That is, does the first sentence meaning imply the meaning of the second sentence, or are they the wrong way around? The second thing that BERT is trained to do is to predict missing words in these sentences. So, how does it do this? How was the model trained? The first thing that the first thing that they do is they take these pairs of sentences and they tokenize them. And they add these special characters, CLS and SEP, in order to indicate the beginning and the end of sentences. These tokens are then fed into the model, and the positionally weighted word embeddings are created for each of the tokens. These are then fed through a series of encoder blocks, and what happens is over time, you essentially get really rich self-attention vectors created. And then the target is, as I said, the model needs to predict whether the sentences are in the correct order, and it needs to try and predict what the missing word is. So again, as with word2vec, as with every model, initially these guesses are going to be really bad, but as it sees more and more examples and gets feedback on where it's gone wrong, the internal weights get better and better, and these self-attention vectors get better and better at capturing the actual meaning of words in context. So I think the original BERT model was trained on around 3 billion words. So you can see it's got a lot of chances to actually learn how language behaves. So this is all well and good, but we don't want to predict entailment or missing words. We want to predict whether headlines are clickbait or not. So what we can do is something that many of you will be familiar with, which is a process called fine-tuning. So we have this model with all these lovely encoder blocks, which have this good representation of how language works. And what we can do is chuck out those last layers that are used to predict missing words and sentence entailment, and use them instead to predict whether a headline is clickbait or not. So in our example, let's take one headline, this one that we've dealt with earlier, and we're going to tokenize it. What we then do is we again retrieve those positionally weighted word embeddings, and we have those encoder blocks that we've already had trained for us. What we then do is simply ask our model to predict whether the headline is clickbait or not. And again, we just do fine-tuning on a little bit of data. We don't actually need that much, and we can get the model to actually come up with pretty good weights in that last layer in order to predict whether, a headline is clickbait or not. So let's see how to do this in Python. So we're going to be working with a package called transformers. You might have heard of it. It's from a company called Hugging Face. They're like super hot right now because they're doing amazing work in NLP. And what we're going to do is first tokenize our sentences. So in order to do that, we're going to use the auto tokenizer method from their transformers package. And before I explain what it does, I'm actually just going to show you what it does. So we run it over our train and our validation data. And what we can see is if we look at the first sentence of our tokenized train data, we can see that we have a dictionary, and the keys are the raw text, okay, the label, whether it's clickbait or not. But we also now have these two new vectors, input IDs and attention mask. So what are these? Well, to explain what these are, let's have a look at what the tokenizer is actually doing. So obviously the first thing that it does is, well, it tokenizes the sentence. There's no real surprise there. So it basically splits the raw text into tokens. It then maps those tokens to a bunch of different IDs. But the problem with this is, and as I said at the beginning, as many of you would know, these sentences cannot be different lengths. So if all we do is tokenize the sentences and map them to IDs, we end up with sentences that are different lengths. So the way that the tokenizer, or the transformers package handles this is by adding a method called padding. So padding basically just adds zeros to shorter sentences in order to make those vectors, or those arrays, the length of the longest sentence. But that brings up an additional problem. As you know, when you're passing those tokens through the model, the self-attention mechanism is going to pay attention to the whole thing. And these zeros don't mean anything, so they're just noise. So this is where the attention masks come in. All an attention mask is an array of the same length as the input array, which has ones for the IDs that should have attention paid to them and zeros for the rest of them. So they travel together through the model and basically tell the encoder blocks, pay attention to this, ignore all of this. And basically the next step is just a conversion of those arrays into tensors. I will not go into that. I'm just going to skip over it. But if you're interested, I will share the notebooks afterwards and feel free to play around with this yourself. And then we can finally get to training our model. So the way that we do this is we read in our BERT model. In this case, we're using a smaller version of BERT called DistilBERT. It's just lighter, but it has pretty much the same amount of accuracy. And we use this method called TF auto model for sequence classification, very succinct. And what that does is it tells the transformer package that we want to read in this BERT model, but we want to throw out the last layer and instead set it up for classification. And that we want to use two labels, clickbait or not clickbait. We set up some further steps, which is basically setting up the learning rate. And then finally, we're ready to train. Again, a very simple one-liner. And what you can see is we've jumped up to a beautiful 99% accuracy. So let's again have a look at where the model went wrong. This is where it was clickbait, but the model did not correctly predict that. And yeah, this is probably a miss. But some of these are, it's a little hard actually to tell whether they're clickbait or not to human eyes. And the same with those that were not clickbait, but the model thought were. I don't know, man, that looks like clickbait to me. So this is actually the point that a lot of these models are at. We're getting to the point where these models can outperform human raters. And it's kind of scary, it's kind of cool. As you can see, it's very easy to use yourself. I think fine-tuning that model took me about 40 minutes on my local machine because I was too lazy to hook up to a GPU. So you can see it's very easy to play with yourself. And that's it. I hope the talk has whet your appetite. Please reach out to me if you want to chat more NLP. I have a blog, lots of NLP posts there, and thank you.